Yeah.
I was thinking about, take notes on,
Yes, I do.
analog, you have to go to.
Now I just straight this load there. It's been very early in here. Or now I want to do this. And I'll get that thoroughly. Yes, I didn't know. So thank you.
Okay, everybody get the exam back? All right, so let's take a look at the had in mind here. So all right. So first problem, most people got this. The problems here were just simple ones with units typically. So, you know, there were a handful of people that just didn't write out the units and didn't have the units right. So that ended up being a problem. And really same thing with this. There were just problems with the units, but those were just you know, involving calculations using these formulas here were you know, back in the back. So one thing too, there were folks that just wrote out, you know, the equation with some numbers, and if there are problems with that, couldn't really tell what it is you were doing. So I want to write out the equation that you're using first, just to help clarify what's up. So the flow net, yeah, aren't you glad that you didn't have to draw a flow net? And I'm really glad I didn't have to grade one too. So. But so what I did was I set up these flow nets using a model. Okay, so the flow net, if the flow net's going to be accurate, except when I put in things in the model that cause it to be off. So right in here, well, so these are the streamlines, the potentials, and the problems are, well, there's a kink here. So that's a problem. There's a streamline that ends. So you can't do that. There are ratio problems here and 90-degree problems here. So those are the main problems. The heterogeneity. So the heterogeneity was probably the one that caused the most confusion. Remember when we talked about heterogeneity, if there's a heterogeneity is a change, contrast in the hydraulic conductivity. And that causes the equipotentials and the streamlines to basically like diffract. So that's it'll be a kink. So this kink right here is a heterogeneity. And I don't know, I think when I did the model, I put in an ellipse right in here. You can kind of see it goes like that. Okay, so that's what I was looking for that problem. Any questions? Okay, so contour problem. 10 meters was a good contour spacing. It gave you what, five contours here, which worked out pretty well. So here's the contours. Probably the most missed was, we talked a bunch of times about drawing contours so that they V upstream. They point upstream when they cross a stream. So you want to have contours like this. And there was also some confusion around the well. This is going to be, I think, the simplest way to draw it. And there are some people that wanted to draw it kind of wiggling around. I don't know. In some cases, it might be possible to do that, but in several cases where people were doing that, it was violating the rules. It was wiggling around, and the wiggling line was going to places that the contour wouldn't go. So this is how it generally. This is the simplest interpretation, and generally with water level contours, you're expecting that the shape of that contour surface to be smooth. So if this is wiggling around, that's kind of a ripple, and probably, unless there's some evidence for that, you want to go with the simpler interpretation. So by far the most points, the most widespread problem on this was these things here. There were way too many folks that had just, had like multiple lines, flow lines coming off of this. This is something that, I don't know, this is something that I've mentioned this several times in class when we did it. And I mentioned it because there just seems to be a compelling urge for people to do this, to draw many flow paths. And because I see it a lot, and so I've tried to mention it several times, but still that urge prevailed. Remember, the flow lines need to be perpendicular to the equipotentials. And if that's the case, there would be an equipotential coming through here. And there's only going to be one line perpendicular to that. So you can only have one line coming out here. You can imagine if you drop a tracer in here, that particle of water is just going to follow one line. It's not going to follow a bunch of lines. So there'll be a problem you'll see problems like this later in the course. So just keep in mind one line coming off of one starting point. The recharge zone is here. This is a big mound. So this is the characteristic of the recharge zone, and there's the well. Any questions there? So here's the 3-point problem. Flux is coming like this. The gradient 15 by whatever that is. I got that number there, about 1.2%. And so for the numbers, 243 and 0.02, then for the flux, what I was looking for is basically that number times the hydraulic conductivity that you got on the first page. And then here, I'm looking for the flux divided by the effective porosity. There are some folks that put the porosity, but it's really the effective porosity. The effective porosity is really the only reason we use the effective porosity is to go from the flux to the velocity. And the reason it's not, there isn't effective porosity, the reason you don't use the total porosity is because when you have flow through a porous medium, not all the pores are utilized by the flow. Some of them are dead end pores, some of them might be low permeability. So this porosity is really, this effective porosity is just the pore space that's used by the flow. So the vertical gradient is 6. You've got a delta of 30 between A and AL, and then the thickness of the sill is 5 meters. So the thing that we need to recognize to get this to work and is that with these two sands, the hydraulic head and the sands is the same as it's uniform over the thickness of the sand. And so the head of the sand applies at the top of the silt and the bottom of the silt. So that's why you divide by the thickness of the silt. And it's flowing down. This is just going to be that head gradient times the hydraulic conductivity of the silt. And then this one, hydraulic head at point D. So this is just going to be going back to the map here at point D, and you have these contours of hydraulic heads. So you're just going to interpolate. So it's really, it ends up being really close to 60. That the contour that you would draw between these coming through that point. Okay, that's it. Any questions? Okay, so what I'd like to talk about today, so this was in the slide deck, this is the conceptual model for the Piedmont. And what I want to talk about today is the continued discussion of wells and the what happens when you pump wells and what is controlling well performance. So talk about some nomenclature, radius of influence, cone of pressure. I'll show you what that means, and then show you basically just want to look at what happens when we pump water out of a well, and what are the physics and what are some of the responses. So let's start with some nomenclature. So here's the well, and we have a pump down here. We're going to pump water out. We'll have some flow rate that the pump is generating. And then what will happen is when the pump is active, it's going to draw the water down, drop the water level in the well. And that's going to cause the water level out here in the aquifer to drop. Now, one thing too that we should keep in mind is that the water level here, this is the hydraulic head. So this could be an unconfined aquifer, and this is the water table. But I think a better way to think about it at this point is to say, okay, the well is screened here, and this is a confined aquifer. So here's the aquifer. And the water is flowing from the aquifer into the well, and the hydraulic head here in this layer is represented by this line. Okay, so we don't have pores draining, we just have this representing the hydraulic head in the aquifer. So what happens then when we drop the hydraulic head in the well is that the hydraulic head in here in the aquifer is going to also drop. And if we think of it right after a snapshot in time, it's probably going to look like that. And then it's going to continue to drop here. And this is gonna continue to propagate out. Okay, so that's the hydraulic head. After we've been pumping this well for a bit. So for some nomenclature. So the hydraulic head have a datum here. So this is the hydraulic head, right? Just the elevation up to the water level. And the hydraulic head is going to be dropping. But typically what we're interested in is not so much the hydraulic head, but how the hydraulic head is changing as a result of pumping. Okay, so this is the change in the hydraulic head. This is, if we think of this as HI, the initial hydraulic head, this is the initial head minus the hydraulic head during pumping. So the hydraulic head is dropping, so it's decreasing, but this is increasing. Okay, because as the head drops, this is increasing. So this we'll call the drawdown. And it's going to be HI minus H. So it has units of length, same as hydraulic head, and it's going to increase as the hydraulic head decreases. So when we pump the well, we drop the water table, we get some drawdown around the well, and the drawdown goes out to here. And then out here, the water level hasn't changed yet. Okay, so this is the radius, the radial distance where the well has influenced the head and the octave. So that's called the radius of influence. And that's going to increase as we pump more. The water level in the well will drop, may drop actually. Depends if we're pumping at constant rate like this, then the water level will continue to drop, and this will continue to expand. Okay, so this has got radial symmetry. So if we take this curve and spin it around, and if we do that, then this is kind of shaped like the bell of the trumpet, kind of a cone shape, but it's going to be shaped like this. And so this is called the cone of depression. Around the well. Remember when we did the flow nets? We had a well and we had the contours around the well, and it looked like that. That was the contours on the cone of depression. And in cross section, the head looked like that, looked like this. Okay, so the gradient is steepening. And that means that the spacing between the contours has to be getting smaller as you approach the well in the cone of depression. Okay, so the drawdown, this is the drawdown in the well. I usually use delta P for drawdown. So this would be delta P, and this would be delta PW. So one of the things that we'll be interested in is how much power do we need to put into the pump to pump the water out? Okay, so the power is going to be, we're going to need to put power in order to pump the water at this rate and in order to lift it up to the ground surface. So the power is going to be let's say, it's equal to a constant times the so this would be 180. Okay, so we need to lift the water from this height up to the surface. And we need to do it at that rate. So if we increase the amount we have to lift it, or if we increase the rate, we're going to need more power. Okay, so it's delta P, the drawdown, plus the initial depth to the water table. And another term that I'm going to use is the specific capacity. And that is that's the drawdown, or the pumping rate divided by the drawdown. Okay, so when we talk about, how much can this well produce? What you hear people say is, well, this is a 10 gallon a minute well, or 50 gallon a minute well, or something like that. But really, the way that it's going to work is the rate at which you can pump water out will depend on what the drawdown is. As you increase this, you're going to increase the drawdown. So you can't really define a well based on just a single pumping rate. It's really this ratio of the pumping rate to the drawdown in the well. Ultimately, we can't have this drawdown get down to the pump, because then we pump air in, and that will damage the pump. So there'll be, in every well, there'll be a certain amount of drawdown that we can do, and then beyond that, we're not able to do it anymore. So this is going to be limited. All right, so there's some terminology. Let's see if I got everything here. Have a slide with these terms on it. Yeah. So this is showing. This is a plot of what the drawdown, the cone of depression looks like. At steady state, the hydraulic head is a logarithmic function of the radius. So that's log of R, that curve right there. And then you take that log of R and spin it around, and that's the shape. And then plot it, contour map, that's what you get. Okay, so there's some terminology. Here's a couple of different ways, or a couple of different reasons why we would want to define or understand well performance. So one of the things we're going to want to do is predict what that drawdown is, or predict the flow rate at a certain drawdown. Predict these two, the relationship between these two. And so if we're going to do that, then we need to know the aquifer properties. If the permeability of the aquifer is high, we can pump more rate for a given amount of drawdown than if it's low. So we need to know the aquifer property. And if we do that and we can predict this, then we can use that to design wells. We can see what the effect of dewatering is on neighboring wells. We can go and understand the impact of these different things. Okay, so that's that's one way to think about well performance. We can turn that around and say, well, this drawdown, this is pretty easy to measure, actually. So maybe we do a test and we measure this, and we don't know this, but we then measure the drawdown and use the well performance to predict the aquifer properties. So we know drawdown with time, we can use an analysis that will allow us to predict the aquifer properties. So this is one of the things, one of the major things that we'll do. We're going to actually go to the field next Friday. We won't be here. We'll go to the field and we'll do this down in the Clemson bottoms. Okay, so these are kind of the hydraulics. How much rate can we pump out? What are the aquifer properties? Another aspect of well performance is the capture zone. So when we have a well and are pumping the water out, that water is coming from somewhere. And the bigger we pump, the bigger the region is that we're capturing the water from. And understanding what that region is important for, well, if you have a well that is producing water for a water supply, then you want to have the capture zone of that well avoid contaminant sources if it's possible. Okay, so understanding what the capture zone is another type of well performance. So we'll do. This is really tracing what the flow paths are to the well. We did this actually, a month or so ago, maybe longer, where we drew those initial contours and then drew in some flow paths, just drew them in by hand. And we could get a set of flow paths that go to the well and a set of flow paths that don't go to the well, that go into the lake. And so that was first cut at defining the capture zone. And we'll do that in more detail with some models. Okay, so here's what happens. This is from a model. There's a well here, and then there's a river here, and there's a monitoring well right here. So this is a plot of the drawdown as a function of time at that monitoring well when we start pumping from that well there. So we start pumping, we're pumping at constant rate, and we start pumping here, and these are the contours. You can see circular contours, and the spacing gets narrower as we approach the well. Okay, and what happens here is the drawdown's increasing as a function of time. And well, it takes a little bit of time here where nothing's happening at the monitoring well, even though we're pumping, but the pressure is propagating outward. So initially we're pumping, but nothing's really happening at the monitoring well because that pressure front hasn't arrived yet. Then it arrives and we start to get some drawdown and it increases. And it increases some more. It's still circular here. And what we see here is that it's flat and then it starts to curve up. And then in this part here, it's a straight line. And this is a log scale. This is a linear scale. So this is a semi-log plot, and it's forming a straight line on semi-log plot. That means that the drawdown is a logarithmic function of time, where it's straight like this. Okay, so that'll be important because we'll utilize that straight line effect in some of our analysis. So what's happening is we're pumping, the drawdown is increasing, we're getting water out of storage. But then as we increase, so this is basically what happens in a uniform aquifer that is at least its lateral extent is infinite, at least as far as the well knows at this point. Okay, but once we start pumping further, remember there's a river right here. Okay, so when the drawdown starts to get close to the river, it interacts with the river. The river acts like a constant head boundary. So when the drawdown starts to come over to the river, it's not going to cause any drawdown over here at the river because it's, it's a constant head boundary. So it's going to start looking like that. And see how it's getting asymmetric? It's getting the drawdown contours, it's flattening on this side and extending out further on this side. Okay, that's because it's interacting with the well or the river. And what happens here is this drawdown curve, it's a straight line, and then when it starts to interact with the river, it starts to flatten out. Okay, flattens out like that. So there it is after it's been pumping for a while and interacting with the river. Okay, so that's kind of the conceptual model. Let's see like why it works that way. Okay, so here it is, we're pumping out, and there we have some drawdown, and we can think of it still in terms of a confined aquifer like I sketched before. So this is just the head in the aquifer. We're not actually draining any pores. It'll work for draining in pores, but let's just keep it simple where it's just a confined aquifer. Okay, so we're pumping at a constant rate, and we've gone just a unit in time. And in that unit of time, we've pumped out a certain volume. Okay, so we have a bucket here. We go for 10 minutes and fill up the bucket. So we have that volume. That volume was stored in the aquifer, and now it's out, and we've recovered. So we've removed that water from the storage. Okay, so remember back a few weeks ago, we were talking about the properties that are related to storage of water and removal of water from storage. And remember storativity? Storativity, what was the definition?
Specific storage comes to well, for the.
Yeah. So what's specific storage? So the storativity, the volume of water released from storage per
Unit head drop.
unit of head drop per
Area.
area of the aquifer. Yep. Okay. So if we, so that's S, right? So this volume that we pumped out in a unit of time is that. So we can do this. So the volume that we pumped out is equal to the storativity, the area that we've affected, right? This area here, and we have delta H. And the way to think about that in this context is that this would be like the average change in the hydraulic head. The hydraulic head is dropping, and the head drop, the drawdown is different, but the average would be something like that. Okay, so that's like delta H R. Okay. All right. So that's the volume that we pump out in a unit of time. And so now we're going to be interested in how this changes with time. So we can do time derivatives, and the rate of change of volume with time, that's just the pumping rate, right? So the pumping rate is that. And if we do the derivative of this, then that's going to be constant. let's just to simplify this, let's hold this constant. It's actually changing a bit, but we'll just to keep it simple, just do this. And we're gonna need to have that because this was defined in terms of head drop. Okay, so the flow rate is going to be equal to the storativity times the area times the rate of change of the head. Okay, so as we pump, the head is going to be dropping. So this will be negative. That gets the sign right. But what's going to happen then is the area that's affected is going to increase with time. Okay, so as this gets bigger, this gets smaller. So if we're pumping out at a constant rate, because we're progressively affecting a larger and larger area, the rate at which the head at which the head is dropping gets smaller. It gets slower. Okay, so this is the head in the well as a function of time. Initially, it has to drop fast, but then as the area gets bigger and bigger, the rate at which the head has to drop gets slower. But if we're pumping water out and it's coming out of storage, this never goes to zero. The head has to continuously drop to get water out of the well. Okay, so that gives us then way to think about or way to anticipate. There's the radius of influence, it's getting bigger, so A is getting bigger. And we have that being the flow rate. So it keeps going. And this is what the head looks like as a function of time here. And then the drawdown in the well is just going to be that with a sign flip. Okay, so this is what the drawdown in the well looks like as a function of time, as a result of kind of going through this logic. What we see here is that there's no steady state in this scenario. If we keep pumping, the head keeps dropping. What we see, though, is that in some cases, the drawdown at wells kind of levels off, and we pump and we don't really see the drawdown increasing. So here's an explanation for that. We start pumping, and for a while, we're getting water just out of storage, and the drawdown is increasing, and the head is decreasing, just like we saw previously. So we have that and that. But this is a shallow aquifer. There's a stream out here, and this is a constant head boundary. We can think of it like that. And as a result of that, when the drawdown gets to here, it's not going past here. Okay, so the drawdown is not going past. I think I got another frame. Yeah. So once you have something like this, here's the head gradient, right? So if the head gradient is like this, we've got flow coming out of the stream. So rather than releasing water from storage, we're removing water from the stream. So that's a different way that we're able to get water out of the this is water going into the subsurface that we then get out. So if that's the case, if the water eventually the water leaving the stream will equal the rate at which we're pumping water out, and those two are equal, and then we can have this go to steady state. So we can have a situation where the head is not changing with time if the inflow from the stream is equals the outflow from the well. And that's what's happening here. Here you see the drawdown is flattening out. That means that it's going to steady state, and we're having flow from the stream going over to the well. Okay, so here's some labels with H, the initial head, the drawdown, and a useful relation here is what's called the time equation, and this describes the hydraulic head or the drawdown in the vicinity of a well at steady state, and sometimes it's written like this as this ratio of logs, but that Ri is the radius of the influence here. And if we're assuming that's constant, then that's a constant, and we can separate this and write it like that. So here this is saying that the drawdown is just a radial function, or a logarithmic function of the radial distance. Okay, so I showed a plot like that earlier. You can see those contours. That's this function here contoured up. Okay. All right. So let's skip over that. Actually, we get time. Do this one a little quicker. All right. So here's a cross section of stream, and the water table between the stream. What happens when we have a well, what I've been drawing is the drawdown cone, and what I drew in those preliminary sketches is the drawdown cone when the water level is flat. But the water level is not going to be flat, it's going to be curved here. This is basically the cross section that I've been drawing since day one. Water table like this. So when we have a well here, it's going to cause drawdown that's superimposed on this curving water table. So it'll look like this. And this is a simulation. So if we have now drawdown look like that, then you can see we've got a divide right here. There's a divide right here, right? The flow will go to the stream. This flow here will go to the well, and then there's a divide right here where the flow over here goes to the stream, and this flow here, this recharge, goes to the well. Okay, so we've started to pump the well. We're just getting water out of storage. Now, though, the drawdown goes over to the stream and hits the stream. But you can see the divide is right here. So we're interacting with the stream. We've reached the stream. This well feels the effect of the stream, but we're not pumping any water out of the stream because we have a divide right here. And the reason we're not is because of this recharge. In that drawing that I showed you previously, without this curvature like this, we would be pumping water out of the stream at this. But really, we're not. The well is influencing the head over at the stream, but it's not actually drawing water out of the stream. But if we keep pumping like that, then you can see we get drawdown enough. This is now drawing water out of the stream. Okay, so you can have a situation where the drawdown interacts with the stream, but you're not actually pumping water out of the stream. All right, so here's another aspect of this. Here's a well, and here's the drawdown around the well. This is the change from the initial head. Well, what if the initial head is sloping? So here, these are head contours. This is low head and high head. And initially the head looked like this. It's all uniformly sloping. So if we take this uniformly sloping head and add to it, or basically subtract off this, then we get contours that look like that. Okay, so if we do a flow net on this, then we get flow that looks like that. And actually, this could be high head and this low head, or the other way around. I think the way I'm drawing this would be the high head, the flow would be going like that. So what we see here is that these flow paths are going to the well, and this one isn't. So the well is capturing water from this zone here. And if we add more flow paths, you can see then that we've got a capture zone. And it looks like this. Okay. Water that gets recharged in there ends up captured by the well. Water that gets recharged here goes, and the flow path is affected by the well. It's curving, but it's not actually going to the well. Okay, so that's an important aspect of well performance. There's the radius of influence of by the drawdown, and there's the capture zone. Okay, the well is affecting the heads in the aquifer over a region that's different than the region where it's capturing water, capturing the recharge. Okay, so that's going to be important because these two things will have different applications. And you can see there's some overlap, but there are also places where both of these things are having a unique area. So this is idealized. Here's some more more realistic capture zones. Here's a well, and the capture zone looks like that. Here's another example. Here's a well with a stream. And you know, what I drew on the previous page was the well interacting with the stream. In a lot of cases, you know, the stream is just a thin layer on top of the aquifer, so the drawdown can go underneath the stream. And in fact, this well is capturing water from beyond the stream. Okay, so these kinds of capture zone analyses are going to form important tools for understanding how to safeguard wells that are producing water from contaminants. They're also going to be important for designing the systems that would intentionally capture contaminated water, like a contaminated groundwater. Okay, so we'll see more about capture zones and radius of influences later on as we look at various ways to analyze wells. Okay, so that's all I have today. Yeah. Yeah, it's
Here's 18,000. It's a 3 days, and it could be anything. That's what I said to them after their quiz, and I was like, thanks for. I said it too, I was like, it made it feel, you know. A little bit cheap plus to get a good grade. I feel like I still have. Probably get the LBO theory. What is it? Achievable. So I got top. Yeah, I mean, exactly. I was doing it for a C minus.
You guys feel all right about the quiz?
Yeah. You're just talking about that.
Yeah.
A lot better.
Yeah,
really.
It felt a lot more achievable.
Yeah.
That's what I was saying. They don't look like, here.
Sometimes it's overwhelming. Yeah, I don't know how the finals gonna be.
Yeah, at this point, I just want to see.
Yeah.
Yeah.
Maybe.
Because I worked it out.
You said it tells me.
A minus.
Yeah.
A, the combination of the A minus. So that's why the ground water. I actually go, I have a word, so it's.
Even if I have a.
Oh.
Yeah.
I have the seminars.
Yeah.
Can't be a defining moment.
Yeah.
I think the hydro students are kind of on the lower end of that class.
I mean, our semester.
Yeah.
Like BAM and Brady, they've seen some of that.
As long as we can get everything together quickly.
I am even more PCs like.
Those two have like the thorough math
Know what I
background
want
to
to
kind
Yeah,
of
do,
understand.
what I want to do. In my senior year, I used to.
I was kind of like.
I started trying to find out.
Out of here and drive and countries.
That's
It's pretty weird. They get the gear all free, and around.
Yeah.
Talk to that.
You will be right from the lady you need to tell them.
No, but.
Oh, what you do, I wanna do here.
Yeah, unfortunately, so what you wanna do, yeah.
Thank you.
So. Hey, Dr. Minock, I got a quick question for you to guess on the homework that's due next week. There's this image on the last page, and I couldn't find any instructions that go with it. Are we supposed to use this for anything?
Yeah, that's the base map for the model.
For which model?
So we're gonna do a model.
There was a different model that we did, and we used a Clemson base map for it, but there are no instructions on this one.
Okay, so maybe this is just leftover.
Okay,
Yeah.
gotcha. Sounds good.
Yeah.
Thank you very
I,
much.
I did use this as this is.
It looks like a similar kind of thing where it had the A, B, and C to get it registered, and then it's got some things that you're working with on
Yeah,
it.
so, okay, so if this is obsolete.
Okay. Sounds good. Thank you very much. You have a good one. Have a good weekend.
Dude,
They don't. Shit. George Street. Yeah. All it up. I'm going. For sure. Why is that different? That distinct from what's in the like. They said, we're gonna be here. We're gonna be graduating. So we're gonna fucking be here. That'll be the way. Look at the end. Anyway, that's what I was saying. I know. That's the branch. We have better chance of getting invited than George Strait himself. That feels good. Might have the next meeting. Get this over. Everything for everything. Oops. So it's not. This is so. Shit all over everything. No bitch. He was listening to English just now. They called. Yeah. Just to make every excuse. Oh yeah. Like my dog had AIDS in my mom. And I had 45 minutes. I'll be able to. Break those and wrote that since he can raise preference. It's totally fun. Yeah. That's
Yeah, what? Yeah, cause like, the other day, she said, I wonder. She said, I heard five people shout. And she even found it. So we have to. She lives up here. Oh. But is it like the? Yeah. Hello? I don't know if she found it.
yeah.
You have a
Like, not listening. It's just.
I need to.
Actually, that was the computer.
Yeah, like that, wait, worse.
Oh,
You just like a sign right there. Like. I don't know. Is that it? So I think it's. So yeah. Do we want message? Maybe okay. Yeah. It's gonna be. Now, how's to be the job? But that's kind of the crap, right? I think it's like I have. So I don't know, but I don't. Like. I'm gonna have to be able to. Yeah, first. You know, already. When you could just like, it's like probably just one day at the library. So we can probably put you on. I really, yeah, we can go down. Yeah. We just meet once. We have this, yeah. It's, I think this is. Well. They're never like. I don't.
Just one bad items.
Oh shit, smells good. Very. Disappeared. Oh. Bobby. Oh. That should be. Like, is it, I don't know, is it supposed to be? Like, yeah, that's something.
Sometimes falls off and left there. Yeah, not a good idea. Still recording, really weird.